Okay, Assalamualaikum warahmatullahi wabarakatuh and very good morning. So in this video, I'm going to explain about the voltage induced in a rotating loop. So when we talk about the voltage induced, actually it can be used for the generator and also for the DC motor. Okay, so as we know that the generator voltage induced in generator when we rotate the coil, okay, the rotor, and yeah, when the coil pass through the magnetic flux, it will induce a voltage. So same goes to the DC motor. So even though the DC motor we supply the power, however the concept of they also will induce the voltage, okay, because there is a magnetic flux and also there is a rotating loop, okay, or rotating coil. So when these two happen, so the voltage will be induced. Okay, so how the voltage is induced in a rotating loop? Okay, so for example, we take this point. Okay, so we take this a single a single coil over here. Okay, so we have a point from A, B, C and D. Okay, so as we know that these two, okay, this AB line, okay, this AB line here, and also the CD is called a conductor. So when one coil or one rotating loop, so they have two conductor. Okay, so this is not count as a conductor, these two position. Okay, so what happen when we rotate, or when the coil or the rotating loop is rotate inside the magnetic field? Okay, as we know that the magnetic field, so we have a permanent magnet over here, north pole and also the south pole. So yeah, the direction of the magnetic flux, okay, from two pieces, okay, from north to south, okay, is not just a straight line. Okay, so if the magnetic field or the permanent magnet is straight like this, okay, so they will be very straight line. Okay, so how about the curve? Okay, so curve over here like this, stator, so the direction is not just straight line like this. It's not straight line like this. This is because the air gap, okay, the reluctance in the air gap is very high, okay, compared to the core. Okay, so in order to pass through, okay, so the magnetic flux will try to go to the shortest distance. Okay, so the shortest distance actually will be happen like perpendicular, always perpendicular to the core. Okay, over here like a perpendicular to the rotor. Okay, so always perpendicular. So you need to remember always perpendicular. Okay, so we have a segment A, B, BC and also DC. Okay, so this is the top view. Okay, so this is the top view. So yeah, so in order to read the voltage, okay, we can do two things. Either we do a slip ring. Okay, so slip ring is like this. We do something like this, and then we connect this to this point. Okay, and then we have another ring. Okay, and then we connect this point. Okay, so and then this will connect with the multimeter. Okay, so and then we will see the voltage when we rotate. Okay, so please be remember that this side is always connect with this point, and this is always connect with this point. Always, no matter the motor is rotate, so this point is always connect with this. Okay, this is not connect with this. Okay, so what happen when we rotates. Okay, at this point we rotate is counterclockwise. Rotate counterclockwise in this direction. Okay, counterclockwise. Okay, so we look over here. So we try to make a summarize or simplify. Okay, so this is a VAB. So VAB, what will happen? So for the induced voltage, so induced voltage is normally we say it happen in the generator. Okay, normally it's happen in generator, and when we talk about generator, we can use the Fleming right hand rule. Okay, Fleming right hand rule. Okay, Fleming right hand rule. So right hand, I will try to draw. So this is the index finger and this is the finger. Okay, they are the two. Okay, so that's the middle lah. Okay, so this is V, B, and also I. Okay. Okay, so this is always perpendicular, three of these. Okay, so we rotate counterclockwise. Okay, so this is the velocity. Okay, and then the direction of the magnetic field is like this. Okay, so what happen when this V and D is B? Okay, try we use the one hand. So this we're using this because we want to find the direction of the current flow. Okay, so V is upward, our thumb is upward, and then to the left, and then this one is will be inward. So inside the page. Okay, will be inside the page, and this one velocity is in this direction. Okay, in this direction, so we can draw like this. Okay, this and this. Okay, V, B. We use our right hand, and this one will be out of the page. Okay, so this is position where V, C, D, and also V, A, B. Okay, this is V, A, B. Okay. So or the otherwise we can use the formula. The formula is E induced is equal to V cross B times with the length. Okay, or we can use also the right hand rule. It's like this. Okay, like current flow. So we cross V to B. Okay, V to B. We cross our finger V to B. Okay, so V to B. So we can, our thumb will show inward. Okay, so this is just to find the direction. Okay, so now we look in the overall view. A, B, B, C, C, D, and also D, A. Okay, so yeah, this is I showed just now. So at segment AB, so segment AB, we use our right hand rule just now. We find out that there is a flow direction for the AB. Okay, so where the positive is in the in. Okay, and yeah, just at the pole of the face. So pole face. Okay, outside no, there will be 0. Okay, so it means that AB we can use our right hand rule. Mean that everything will be in the perpendicular. V, B, and also the I. Okay, so everything should be perpendicular. So if one of them is not perpendicular, that means the result will be 0. Okay, so now segment BC. So segment BC, so from here a little bit difficult because not difficult, but the point of view. So here I want to draw is a bit difficult. Okay, so the simplest way we just look over here. So BC. Okay, BC actually is the same direction with the B. So mean that the length or the wire is actually in the same direction with the B, the magnetic field. Okay, so when B is same direction, it means that there is no perpendicular, it is not perpendicular to everything, so the result will be 0. Okay, so it is mentioned that the VB is perpendicular to the L, the wire. Okay, and then a CD. Okay, CD, then now we can see we can use the whole right hand rule. Okay, so V is downward and B is to the left. Okay, and then we can get the current flow. Okay, where is outside the page. Okay, the tip is very simple. You need to remember that everything must be in perpendicular. Okay, everything must be perpendicular. Okay, then segment DA, so same to the BC, where the length of the wire is in line, okay, with the B, okay, with the vector B, the magnetic field. So there is no current induced or voltage induced at these 2 points, the BC and also AD. Okay, so then we total up. Okay, we total up everything, segment AB, BC, and also CD, and also the DA. Okay, we total up the voltage induced. Okay, and we got what we get here is induced voltage is equal to 2VBL. Okay, so under the pole of phase and beyond will be 0. Okay, so over here actually it's difficult to measure the velocity. Okay, so or we want to simplify the voltage. Okay, simplify the equation to the more meaningful or to more understanding equation. Okay, so as we know that the V, okay, the velocity is equal to R omega, okay, R omega, which is the angular velocity. So we replace the V. Okay, so we replace with R and also the omega. However, in here also we can try to simplify. We can simplify it to the more meaningful. Okay, so yeah, over here we try to replace, okay, to replace the or summary the equation to the more meaningful. Yeah, as we know that the rotor actually is cylinder. Okay, in order to get the cylinder, the area over here, it actually is 2 pi r. This is 2 pi r is a parameter. 2 pi r times with the L. Okay, so A is equal to 2 pi r L. Okay, so however, to find the pole, okay, area of the pole, okay, actually the formula is like this. AP is equal to 2 pi RL divided by number of pole. Okay, divide by number of pole. So in this case, we have 2 pole. Okay, so we have 2 pole, not south. So this is the rotor. So we have 2 poles. Okay, so we have 2 poles. So the position, the area of the pole will be pi RL. Okay, AP. Okay, so AP is equivalent to pi RL. Okay, so over here we have R and also L. Okay, however we can divide by pi after this. Okay, we also know that the flux is equal to pi AP over B. Okay, so pi equal to area times with the B. Okay, so then we replace the A first. Okay, so we have pi RL, so we have like this 2 and then A, P, B, omega divided by pi, because AP is 2 pi r. Okay, we have RL, so pi, so we need to divide. So when we divide pi, so we get back the RL. Okay, so then we have APB. So this we can replace with the flux. Okay, so now the formula, okay, the final formula for this, okay, induced voltage is like this. Okay, so this is in the case of only two poles, for two poles and one rotating loop. For one rotating loop. So how about the there is a many loop, okay, multiple loop, okay, the N loop. Okay, so later we will talk about this. Okay, so sometime we can summarize that this, okay, this actually is a constant, okay, for the construction of the motor. Okay, so this is we can replace this as a K, and this is flux, and this is the omega. Okay, sometimes we can write like this, E equal to K phi omega. Okay, so later on we will talk about the construction of the motor. Okay, so in general you can say that the voltage is in any real machine depend on the three factors. Okay, so the first one is the flux. Okay, so this is the flux. Okay, when you increase the flux, so the voltage also will be increased. Okay, okay, and then the speed. So when you rotate faster, okay, you increase the speed, you will get the higher induced voltage, and also the constant representing the construction of the machine. Okay, so if the value of K is higher, okay, so when K higher, so you rotate slow, you also will get the higher induced voltage. Okay, because the K or the construction is well designed. Okay, okay, so after all, okay, when you just now I showed that you put the multimeter. Okay, so just now I do two like this, two slip ring over here. Okay, and then you measure multimeter. Okay, you put multimeter here. So when you rotate, okay, so this point is always connect to this point. Okay, for example, this is a red color in the multimeter, and this is the black color. Okay, so when you measure here, so when this rotate 180, okay, this is CD and CD. So when you rotate to the CD, okay, what will happen? Okay, CD, okay, I try to redraw this. Okay, so now here is D, now is C, B, A. Okay, so draw two rings, and this is will connect over here. This is will connect here. Okay, this is connect, and then this is connect to the multimeter. Okay, so what happened here actually, so just now we can say that the current flow, okay, I show you again the current flow. Okay, so here for example here, okay, so we take first the so VAB, first here VAB, okay, EAB, the EAB. So we use the Fleming rule, so we get the over here is, so the current will flow like this, okay, and then like this, and then like this, okay. So the total out will be so this will be positive, okay. So what happen when you rotate 180? Okay, so they rotate like this, okay, to the counterclockwise, okay. When you rotate counterclockwise, same goes to here, okay. So now the current will also flow like this, okay. DC BA over here, okay. So DC, so now here after rotate, the DC will be replace the EAB, okay. Now this is DC, sorry, DC, okay. The VBA over here will be positive, okay. So it will go like this, okay. So this will become positive part, okay. So at total there will be a it's like a AC, okay. We will show you like a AC voltage, okay. So yeah, in order to get the DC value, okay, in order to get the DC value or DC voltage, okay, so in order to get the DC voltage, the position, okay, the direction or the current flow for the each for example the coil, so the coil will always the current will flow always at the same point, okay. For example this A to B, okay, A to B, okay. So here once we rotate, there will be B to A, okay, because there is no other changing, okay, to the split ring, because they always connect together, okay. So in order to do that, we need to split, okay, we need to split this one, okay. It's like sometimes this one will connect to here, sometimes will connect to here, okay, they will change, okay. In order to do that, we'll do a split ring, okay, or the other name is like a commutator, okay, the other name is a commutator. So over here you can see when the rotor rotates, they will connect to this point first, okay, and then when it rotates, they will split, then they will connect to this commutator, okay. So therefore the current flow will always be positive, okay. So we can say that we can have like very straight line, very constant, okay. When we check to the multimeter, they will give you a constant value, okay. However, in the real life, actually they will give you like this, okay, up and down, okay. Okay, I think that's all for the video. So later on I will show you on how to measure or to calculate the K for the constant or for the construction of the motor. Thank you.